Thank you. So yesterday, when I feedback Neil to say that at least here in the Bay Area, I can think about at least 300 companies or more attendees that the conference is in the right context. I realized that, of course, Neil has this, I would say, mission, yes, to bring the industry together, to identify gaps, and to talk about ecosystem. So instead of diving to an ultra-technical presentation, I did ask marketing to help me with somehow a more broad presentation, and then, of course, to dive deep. Because we are, only 75 employees, and we do only one thing, compression. So very narrow, but very, very deep. So I'll try to make myself first wide and then to dive slightly deep. What we can see in the industry is a growing gap that needs to be bridged, and it fits, as I said, into Neil's vision to bring the industry together. Okay.
Actually, it's not just my vision. It's Intel and Advanced Micro Devices and a slew of other companies that are interested in doing this kind of thing.
That's true. So we are almost, we are 10 years old. 4 years, almost no business and only scientific research. And we have, a few but very important customers like Netflix, Microsoft, Azure Media, and a few top cable companies and telecommunication companies that we cannot use the names, but I would say the leading streaming, OTT streaming media and pay TV customers. Offices in Tel Aviv, Palo Alto, and St. Petersburg. The gap that I really want to talk about is what's going on between the capture industry, the display industry on the other end, and we somehow, the compute industry, in between. So that's really a visual representation of maybe 50% of the current smartphones that are already with 1, 2, or even 3 4K sensors, 4K P60. And 1 minute of 4K P60 equates to 400 megabytes, 400 megabytes, 1 minute. So we can also see that the display industry, Samsung plans to sell more than 1 million 8Ks, and 50% of US households already switch to 4K. And essentially, if you go to Best Buy or Amazon, you can buy only 4K TVs. You cannot buy HD TVs. In terms of broadband, this is a nice representation of the top cities and bottom cities in terms of broadband. But as I said, you can see that 50% of the market already switched to 4K in terms of the display. But you can ask yourself, where is the 4K content? How many Fox Sports or ESPN channels you can see in 4K? Most of them are still HD and, of course, all the news, etc. And at top and beyond and above, of course, you can ask yourself as a user, what do I do with my 4K? Because once again, it is handy. I can take 4K today. But as I said, 1 minute is 400 megabytes. And how many of you will pay the iCloud or Dropbox or whomever to retain the original resolution? And as you know, once you upload to Facebook or YouTube or whatever, if you did, 5 megapixels to Facebook 6 or 7 years ago, it was shrink to 1 megapixel. You take a picture of your daughter or whatever, 20 years later, you ask yourself, where are the pixels? Because, pixels that were lost forever. Once again, statistics. So more than 75% of the smartphones already are capable with 4K sensor, CMOS sensor. 75% of the iOS can support native HEVC in hardware. This is the next generation codec. This is the more advanced codec. More than 50% of Android devices support HEVC in hardware. And we assume that UHD TV, the display, will be more than 60% penetration by 2022. Now, in Tokyo, so, you know, we just closed a small deal of 8K channels with customers that are preparing to the Tokyo Olympics. And NHK, the Japanese broadcast authority, will deliver at least the contribution signal will be 8K. So it looks like we are switching, you know, from HD to UHD to 8K, almost at the same pace that they changed the emperor. They are already at 8K, and we will be at HD here. So that's something that we notice in the industry. There is a growing gap between the capture and the display. Capture and display are already mass market in 4K, but the lifetime permanent storage and the streaming services are primarily with HD. And that's, of course, where we come to play, because, you know, we are the compute industry. So what is needed for 4K and 8K delivery and, as I said, lifetime permanent storage? There are many aspects, and of course CDN and caching and peering services, and we are just a compression company. But of course compression is very critical here. And I want to at least bring as a company, our two critical contributions to the industry. The first one, of course, is density, which means how many channels you can fit into one server. And that's where we have great partnerships with our main sponsors here, Intel and AMD. So that's, two announcements that we have made together with Intel and AMD. One with the new AMD EPIC-ROM. Finally, we were able to fit 8K into a single socket. So these are, mega sockets, 64 physical cores, 128 hyperthreads, but we were able to fit 8K, 60 frames per second, 10 bits into live broadcast quality into a single socket. And that's another announcement that we did with Intel. This was a while ago. With the Intel Scalable Platinum to fit really 6 4K profiles into, once again, a single machine. Now, that's not easy as it sounds, because, in encoding, if you know encoding, you have predictions, and you have I-frame and B-frame, and the B-frames are extrapolated from the one before and the one after. And of course, then you need to do the quantization and the entropy coding, and you always have something that is waiting for something. So here Intel and AMD came with marvelous machines with ultra high core count, and they are available for everyone on AWS and Azure for $3 per hour, etc. But what do you do with those cores? So that's just a Linux htop command. In this case, it is running on an Intel 8280. This is a machine with 56 physical cores and 112 threads. And what you can see here is that we are using all the cores all the time, or 96% of the time, 100% of the cores. And as I said, if you will try to check your encoding utilization of the cores, you will find out with open source that sometimes 40% or 50% of the cores are using, and you always have cores that are in idle. So you have a tremendous compute power, but you don't use it to the maximum. And that's this high utilization is based on a very smart algorithm that breaks the encoding into thousands of tiny microprocessors and asynchronously scale those processes all across the platform, all across the 56 or 64 physical cores, or in a dual circuit machine across 120 cores. So the performance, this is just a benchmark of HEVC compared to an open source, and you can see that with this architecture, we are able to deliver 60 or 50% more throughput from the same given server. So in one end, you have the full ABR stack with 5 layers, and in the other end, you have the top profiles. So we are moving from HD to 8K, and the consumers already hold in their pockets devices that are capable of capturing 4K. So 8K is basically 32 megapixels per frame. Even today, an SLR, a professional SLR camera can be satisfied with 32 megapixels per frame. So now I want to, so this is, in terms of throughput, how many, or the ultra fast pace that the display industry and the capture industry are keep adding more and more pixels that we can barely, fit into our compute platforms. Now, I would say more critical contribution to the industry is CABR. CABR stands for Content Adaptive Bitrate. And that's basically a standard encoder that is based on standards. There is no special decoder at the receiving end, but CABR is basically control or the rate control frame by frame, adjust the quantization or the bit rate to represent human vision. So if somebody takes a video of us here together, you can assume that on the ground, on the floor here, you have frequencies that are way beyond the human vision. So I want just to show you how it looks with a short demo. I want you to see when I'm flipping between those images, and I will just also open for you the info window. So you can see that this image, you can see that I'm now pointing with my cursor. It is, this is an SLR image, 26 megapixels, and the file size is 11 megabytes. This one is the same resolution. It's the same resolution. You can see that it's the same resolution, but the file size is only 1. So this is 11. I'm flipping now in front of you between 11 and 1, 11 and 1. But it looks the same. It looks the same, and even if you come from a very close or normal viewing condition, it will look the same. Now you can tell me, Eli, this is a very rich file. Can we see the full resolution? So we can do the same and go to the full resolution. And here I am flipping between 1 and 11, 1 and 11. And it looks the same to you. So this is content adaptive encoding, it is very clear. You can understand, of course, what's going on here. Here, of course, you can see that there are frequencies that are way beyond your vision as human. So the CMOS sensor, of course, is designed to capture all the photons, but this is not how your brain works. Yes, your brain gives different priorities, and there is a limit, yes, to the frequencies that you can perceive. So let me now, just to understand how it works, I will open another pair of images. And here you can see that this one is the content adaptive. It's 994 kilos, 1 mega, and this is the original, and the original is 3.3. So in this case, we saved 60%. Not 90%. 90% of this is, of course, extreme. But the point is that this algorithm commits only to the quality. It is based on a quality measure. That's what we did in the last 10 years, to develop a quality measure that perfectly represents the human perception for image quality. So that's how content adaptive works. In images, and of course in video, it's frame by frame. And here I want to show another example. This example is very, very important because every pixel that you see here was not compressed by us. It was compressed by the new Intel Gen 11, the Ice Lake fixed function compressor that is part of the platform. But the Ice Lake, what Intel did for us, they did allow us, they developed a special interface in the media SDK that allows us to use the CABR controller and to control the Intel device, the Intel fixed function. So why this is important, or very, very important? So this is our stereoscopic player. By the way, this is a tool that we give free to the industry. It's basically a stereoscopic player that you every video expert, or many, are using this tool. It is free. You can go to Beamr.com and get it. But it allows you to basically move the slider and check quality and overlay two encodes. So here you can see this is like Stadia recipes, but you can see that in one side here it's 12, and in the other side it's 21 megapixels. And of course this is a recorded clip, so I'm not playing with the slider, but the quality is identical. The 12 is perfectly identical to the 21. Now, this is very critical because this is just a POC. And the point is that what we have made into a successful business with media and entertainment companies that are using the very powerful Intel scalable Platinum, etc. This is not applicable for user-generated content. If I'm taking a wedding or a bar mitzvah or a birthday of my son or whatever, I cannot run a machine with 32 or 26 physical cores on AWS to compress, to do this kind of smart analysis. So the point was, can we use silicon? Can we use hardware encoder? And if you're using Adobe Premiere or Final Cut Pro, you can see that basically those software machines, when you export the video, they are not using the Intel fixed function or the AMD fixed function or the NVIDIA. They are not, because these fixed function encoders, they were not smart enough to make the right decision of the bitrate and the quality combination. So they are fast. The density is very good, and you free the general purpose cores that you have on the machine, but the outcome is not good. So Adobe and others, they move to software encoding. And for this, when you run on the cloud, you get, of course, you can go all the way to real time, but these are very expensive machines, and the gaming industry and the user-generated industry were excluded. The ROI doesn't fit, so of course the user-generated, and they shrink, they resize, and they don't save or stream or share the full resolution of what you have captured. In this demo, everything was used with the, I don't know what is the side, maybe you, of course, can Intel, of the fixed function encoder, but it's like 2 square millimeters. It's very small part of the chip. And everything else, the GPU, the CPU, is still available for you. So in this case, the CABR in software controls the Intel silicon fixed function, and you get yourself a client, a desktop technology that can do this very smart CABR encoding, and not just powerful servers. So this is just a demo, and if I go back to my presentation. So now, how do we do that? So for this, of course, we need to, as I said, to measure image quality in such a way that represent humans. So this is, in this example, we see two images that, give or take, for most users, they look the same. But we are looking at two very important quality measures that are very accepted in the industry: PSNR, peak signal-to-noise ratio, and structure similarity. And you can see that although the images, MOS is mean opinion score. This is us, human. There is a protocol that you check image quality with humans, you show them an image, a gray screen, another image, and you ask them to identify the impaired image. If they are right 50-50, it means that it's identical, they are just guessing. So MOS is the human score, and it is 5 is the best, 1 is worse, and in this case it was rated as 4. SSIM less than 39, PSNR less than 39 or 38, it's considered to be good, bad quality. And in this case, human did agree that this is good. The images, they are not high quality images, it doesn't matter. But the original and the compressed, they look identical. Yet you can see that PSNR didn't rate them in such a way that represent human. The Beamr score, 0.35 to 0.5 means good. So, and structure similarity, again, less than 0.96, it's low quality. So PSNR and the SSIM rated those two images as low quality, although human did appreciate the compressed to be near identical to the original. So these quality measures that are so prevalent in the industry are not good. Here, I don't know if you can see, but I think that you can see. Yes, you can see. Everybody can see that in the compressed image, you can see the bending. They are very clear. Do you see the bendings in the compression? I think that it's very noticeable to see the bendings. And of course, human did identify the artifact, and it was rated in a very low quality. The Beamr score dropped. Unfortunately, PSNR and SSIM both jumped very high to represent very good compression. So this was the key point in our research, to build a quality measure that can represent human, but it's also very fast. It's not based on very heavy machine learning or very expensive algorithm, because once again, if we would have something that is heavy, we exclude the gamers, because in gamers, we need a stream per user. So every stream needs to be compressed, and we need something that is light. So our quality measure algorithm is essentially, it is based on tiles. It is codec agnostic. It can work with AV1 and AVC and VP9 and HEVC and VVC in the future. Every block-based encoding, every DCT-based encoding today or tomorrow, we can implement CABR. And essentially, you can see, some of the things. First, the measures, we do the measures in tiles. You can see that, we identify skin tones and edges and areas of interest. But the most important part is to do the pooling. When you have all the scores from all the tiles, there is an algorithm that eventually makes the decision good or not good, or give the frame score, and how to pull all the scores from the various tiles. That allows you, of course, also to go parallel and to reduce no or negligible latency. This is really a process that took us many, many years. And to do this, we are using a tool that we have developed. It is based on Amazon Mechanical Turk. And we can recruit hundreds of humans, and we can use them to test and train those algorithms and to calibrate the coefficients, et cetera, We have to pay them $1 or $2 per test. But once again, that's the way that you build a quality measure algorithm that is representing or fully correlated with human perception. As I said, this is the critical, the tile, the score pooling that is, and all the artifacts that we measure, and we give them wages, like texture and similarity, et cetera, et cetera. It is done in tiles. Now, you can see the impact on a video. So it's not just that it lowers the bitrate, it also suppresses the peaks. And that's where usually you have the rebuffering events. And this is something that is very critical for user experience. So the CABR encoding, of course, is slightly heavier because you do this quality analysis. And you make decisions, you create candidates frames, and you make decisions based on the quality measure. But the bitrate is, the user experience in streaming is much better. You get and of course, if you are connected with the mobile medium, if you are over LTE, etc. So that's really maybe a good representation. And you can see that, this is CABR against VBR. So, to begin with, in those codecs, there is, of course, a very smart algorithm that is based on variable bitrate. The encoder also makes smart decisions and, of course, can do predictions and copy from frame to frame. So when you give the encoder a slack, yes, for a VBR, the encoder will try to do the best to accommodate the bit stream to the best encoding possible. But of course, the higher is the quality or the higher is the bit rate, that's really today your best strategy. If you want higher quality, you increase the bit rate. And what CABR is doing essentially is shaving or taking all the redundancies beyond the human vision. And the higher is the quality, the more, the higher is the contribution of CABR to the experience and to the efficiency. So, as I said, the Beamr part, when we did software-only solution, of course, we made everything from scratch. The encoder, this is our encoder, the very high-performance encoder. But the CABR control essentially can control an external, a hardware encoder, and that's what we did with Intel. This was demonstrated at NAB, the video show, and IBC in Amsterdam, and most likely you will see this very soon as a product in other trade shows. But the point is that it is agnostic, and it's really a tiebreaker, yes, between all the silicon encoders to bring a wisdom of a software encoder to a fixed function silicon encoder and reduce the total cost of ownership or the cost per stream in such way that really fits user-generated content. As I said already, it is essentially based on artifacts that are part of block-based encoding, so it is applicable. We have right now implementation that is working with AVC and HEVC, but it is applicable to VP9, AVC, VVC, etc., etc. So it's like future proof. As I said, CABR commits only to the quality, so it takes the reference encode that your VBR encoder did and present an identical quality at lower bitrate. So CABR cannot commit really to the saving, but it is safe. You don't need a human to do quality assurance. It is always safe. The quality is always identical at the output. In a cloud gaming application, of course, it is very critical. You did see the information that Google published in terms of expected bitrate for various resolutions. And if you try to match it with the availability of broadband services, mobile and landline, you can see that, of course, there is huge gap. And as I said, this gap is continue to go in front of our eyes. That's, as I said, the numbers that came from Stadia, and obviously, if you take 35 megabits per second as an average required service, you can see how few can enjoy this kind of experience. So that's what, just using the numbers that cloud gaming is in a very early stage. But as I said before, this is true also for user-generated content. When you do your Facebook Live or Twitter, Periscope, etc., in your hand you have a device that can capture 4K, and you'll find out that you share 480p or SD, although you can capture 4K. And these are, some of the examples. These numbers, once again, they came from our collaboration with Intel, with the CCG group, and this is, few titles that we checked together. And you have the VBR encoding. So every pixel was done by the Intel. So this was what the Intel was set to 21 megapixels. And you can see that, of course, our savings are not consistent, 16, 14, 13, etc. As I said, it is designed to be identical, but yet they are very significant. All the way 25 to 40% significant savings. And once again, it is using a tiny piece of the Intel Gen 11 Ice Lake processor. So that's good news because the GPU is available for you, the CPU is available for you. The power envelope, of course, is reduced. So for me, using CABR, it's almost like driving a Tesla or an electrical car. If you have bits that you don't need, take them off the stream. You clear the information highway. And if you use smarter or better compute and algorithms, you enable a much better user experience. And user-generated content, those lifetime permanent memories and storage, if you capture 4K today, it looks amazing. You visit your memories in 15 years on a 32 or a 16K TV, and it will look like a shrinked. So keep your memories in the full resolution, the original quality. That's CABR. This is our little contribution to the industry. And as I said, Neil, in front of our eyes, there is a growing gap between capture, display, and we are in the middle. We definitely need to do a better job. So that's who we are. Only compression, but it's important. Thank you.